In the world of engineering, different disciplines often intersect and collaborate. Electrical engineering, focused on the study and application of electricity, electronics, and electromagnetism, might seem worlds apart from mechanical engineering, which deals with the design, analysis, and manufacturing of mechanical systems. However, understanding basic mechanical engineering principles is crucial for electrical engineers, especially when working on systems that involve both electrical and mechanical components. This lab manual guide aims to provide a concise overview of essential mechanical engineering concepts tailored specifically for electrical engineering students. By exploring practical examples and real-world applications, we will shed light on how a fundamental understanding of mechanical principles can significantly enhance problem-solving abilities in the field of electrical engineering. From power generation and distribution to robotics and automation, the integration of electrical and mechanical systems is ubiquitous. Therefore, bridging the gap between these two disciplines is not just beneficial but essential for aspiring electrical engineers. A prime example of the interplay between electrical and mechanical engineering is the operation of power plants. Steam boilers, massive vessels that generate steam from water using heat, are fundamental to this process. Understanding the principles of heat transfer, fluid mechanics, and thermodynamics is crucial for electrical engineers working on power plant design, operation, and optimization. Similarly, steam turbines, which convert the thermal energy of steam into mechanical energy to drive generators, exemplify the seamless integration of mechanical and electrical systems. The rotational motion of the turbine, governed by principles of rotational dynamics and fluid mechanics, is what ultimately enables the generation of electricity. Temperature measurement and control are essential aspects of many electrical systems. From monitoring the temperature of transformers to ensuring the optimal operating temperature of electronic components, accurate temperature measurement is paramount. Various types of temperature measurement devices, each operating on different mechanical principles, are employed in these applications. Thermocouples, for instance, utilize the Seebeck effect, a thermoelectric phenomenon, to generate a voltage proportional to the temperature difference between two junctions of dissimilar metals. Understanding the working principles of these devices, along with concepts like thermal expansion, heat capacity, and thermal conductivity, is essential for electrical engineers to select the appropriate temperature sensors, interpret their readings accurately, and design effective temperature control systems. The synergy between electrical and mechanical engineering extends far beyond power plants. In robotics, for instance, the design of actuators, the muscles of robots, requires a solid understanding of both electrical and mechanical principles. Similarly, the development of electric vehicles necessitates expertise in both domains, encompassing battery technology, electric motor design, and vehicle dynamics. By grasping fundamental mechanical engineering concepts, electrical engineers can effectively communicate with mechanical counterparts, collaborate on interdisciplinary projects, and develop innovative solutions to real-world problems. In an increasingly interconnected world where technological advancements are blurring the lines between traditional engineering disciplines, a holistic understanding of both electrical and mechanical principles is invaluable.